and welcome. Today we'll be solving another important question on points of contraflare. All right, you can see the question on your screen, and the question says a beam is 10 centimeter long and it's carrying a uniform distributed load of 1 kilonewton per meter, and it is having two supports which are 6 meter apart. So we want to find the position of the beam where the bending moment is as small as possible, and then we are going to be drawing the shear force and the bending moment diagram. So that is just the question. This diagram will not be provided for you, so you use the information on your screen to draw this diagram. All right, so you can see I have drawn my diagram on the board. So here is my point A, here is my point B, here is point C, and here is point D. All right, you can see I've put my parameters. From point C to D is 10 centimeter. The support is 6 meter apart, and you can see the uniformly distributed load is 1 kilonewton. All right, so for us to start the solution to this question, the first thing we are going to do is this. We don't know what the distance from here to here is because we are not given from the question. All right, even we don't know the distance from here, but we can say let this point to be what? S. So if this point, if point AC is S, so it means we can know what point BD is going to be. All right, so since from this point to this point is 10, this point to this point is 6, this point is X, so this point is going to be 10 minus 6 plus what? S. All right, 10 minus 6 plus 8 is going to give us what? 4 minus S. So it means this point is going to be 4 minus S. All right, so we are going to have that point to be 4 minus S. All right, so the first thing we are going to start with, the summation of our upward force to be equals to downward force. So we are going to take summation of force in the y direction to be equals to 0, and we are taking our upward force to be positive and our downward force to be what? Negative. All right, so this is what we are going to be doing. All right, so our upward force is positive. So the two upward force we have here is reaction at A and reaction at B. So we are going to say reaction at A plus our reaction at B should be equals to, all right, so our downward force now, we are going to convert this uniform distributed load to a point load, and of course it's going to be a what? A downward force. All right, so how do we convert this uniform distributed load to a point load? We are going to multiply the weight of this uniform distributed load by the total distance that it covers. So we have 1, so it's going to be 1 multiplied by 10. All right, so we can therefore say reaction at A plus our reaction at B will be equals to 10. So let's call this our equation number 1. All right, so the next thing we are going to do is to take the summation of moment about point A. All right, so we take the summation of moment about point A to be equals to what? 0. All right, so this is my point A, and you are going to take note of this point here carefully. All right, this is my point A. All right, so if I want to take the summation of my moment, I'm going to have first ROB, right? ROB multiplied by what? By 6. So don't forget, we've already said our upward force should be positive and our downward force should be what? Negative. If you have been following our series of videos on on bending moment and shear force, you are going to note by now that the if we say upward force should be positive, it means the moment created by this upward force will also be what? Positive. If we say our downward force should be negative, the moment created by the downward force will also be what? Negative. So if you look at our upward force here, it's going to create an anti-clockwise moment. So it means this anti-clockwise moment here is going to be what? Positive. All right, so now it means that ROB multiplied by 6. So we are going to have ROB multiplied by 6. All right, so now don't forget that here if we take our moment towards this side here, it's going to be a what? An anti-clockwise moment. So again, at this our point A, if I stand at this point A and I'm taking moment towards this side, don't forget that we said that clockwise moment is the same thing as what? Anti-clockwise moment. Or anti-clockwise moment is the same thing as what? Clockwise moment. So the moment that we are taking from this point towards this point A here is also going to be what? A positive moment. All right, so we are going to say plus. So this is the point I'm standing. So if you look at this, we are having a uniform distributed load. So it's going to be, we are going to convert to a what? To a point load. So it's going to be 1 multiplied by what? S. So it's going to be 1 multiplied by S, then multiplied by S divided by 2, because S divided by 2 is the total distance that is going to cover. All right, so this will be equals to, so now again we are at point A. Now what is the distance from this point to this point? All right, the distance from this point D to point A is going to be what? 10 minus what? S. 10 minus what? S. So from A to D is going to be what? 10 minus S. All right, so don't forget we are having a uniform distributed load again. So this is going to be 1 multiplied by the total distance it covers, because we are going to convert this uniform distributed load to a point load. So for us to do that, we are going to multiply 1 multiplied by total distance that it covers, which is 10 minus S. 10 minus S. Then the distance that it covers now is going to be multiplied by 10 minus S divided by what? Divided by 2. All right, so now the next thing we are going to do is we are going to solve some maths here. So here we are going to have 6, all right, plus S squared all over 2, then which will be equals to 10 minus S all squared divided by what? Divided by 2. All right, so that is what we are going to have. All right, so here we can multiply through by 2. If we multiply through by 2, 2 multiplied by 6 RB, we are going to have 12 RB. Sorry. All right, so we are going to have 12 RB. All right, so if we multiply this by 2, we are just going to have S squared. All right, so which will be equals to, so if we multiply what we have here by 2, we are just going to have 10 minus S all square. So if we open this bracket, you put your square on 10, we are going to have 100. If you put, then we are going to say 10 multiplied by minus S multiplied by 2, we are going to have minus 20S. Then if you put your square on negative S, you are going to have positive S squared. All right, so if you look at this carefully, this S squared, we cancel out this S squared here, then we'll be left with what? We're left with 12 RB equals to 100 minus 20 minus 20S. All right, so now if you look at this, 20 is common, we can factor out 20. So I'm going to have 12 RB to be equals to 20 into, so if you remove 20 from 100, I'm going to be left with what? 5 minus S. All right, so for us to get our reaction at B, we are going to divide both sides by 12. All right, so our reaction at B will be equals to, here we know that 4 can go in 20 to give us 5. 4 here is 3. So here we are going to have 5 into 5 minus S all over what? All over 3. All right, so this will be our reaction at B. All right, so how do we get our reaction at A? All right, let's go. So now from equation 1, we know that reaction at A plus our reaction at B will be equals to what? 10. All right, so if I substitute for RB here, it means that RA will be equals to 10 minus RB. So it means that our reaction at A will be equals to 10 minus 5 into 5 minus s all over what? All over 3. All right. So our reaction at A, therefore, will be equals to 3 times 10, that is 30, minus, so if I clear this bracket, I'm going to have 25, then plus what? Plus 5s all over what? All over 3. All right. So if we continue with this, we're going to have our reaction at A to be equals to the reaction at 30 minus 25, that is 5. We're going to have 5 plus 5s all over what? 3. So which we can further write as RA to be equals to 5 into 1 plus s all over what? All over 3. All right. So we are done with reaction at A and reaction at B. All right. So the next thing you are going to note carefully is this. All right. The question says, so that the bending moment will be small as what? Possible. We want to find the position, you understand, of the beam so that the bending moment will be small as possible. All right. So you will need to understand this concept I want to explain. All right. Now, if you have been following our videos, you know that if we have an overhanging beam, you know this beam is an overhanging beam. How does the bending moment diagram of an overhanging beam looks like? If we have, let's say we have something like this. So this is let's say, all right. So the diagram can look like this. All right. So most at times this is how the diagram looks like. All right. Or sometimes it can look like this, depend on the question. All right. It can look like this. All right. So now, but here's the concept I want to explain. All right. Now we know that this is where we have our maximum, our positive maximum bending moment, and here we have here to be our what? Negative maximum bending moment. How? Because you can see this curve here is it is, let's say, it's greater than what we have here. If you look at from this point to this point, is greater than from this point to this point. All right. So the concept is this: our between the span, you know, this is let's say this is A, this is B. So maybe this is our reaction at A, this is our reaction at B. All right. So in between this span, we have our maximum positive bending moment, and at the support of this beam, we have our negative maximum bending moment. So for this overhanging beam to be small as possible, it means that we need to adjust the length so that the maximum, the positive maximum bending moment at the span of this beam will be equals to the negative maximum bending moment. Do you understand that? So we will need to adjust the length of this beam. So by the time we have the equality sign, it means that the bend moment of this overhanging beam will be small as possible as the question required. All right. So the next thing we are going to do now is to take this concept that I just highlight here to solve the question now. All right. Now, you are going to note again that our bending moment is going to be maximum. I think we are going to have our maximum positive bending moment within the span AB. All right. And it's a positive maximum bending moment there. And we are going to have our maximum bending moment where our shear force is equals to what? 0. All right. So for us to continue with this calculation, we are going to be taking a distance from the center of this beam to what? To point C. All right. All right. So let's call it distance Y. All right. Let's call it distance Y. So the first thing we are going to be considering is we are going to be considering the shear force at section AB. Section shear force at section AB. All right. So let's just take that to be shear force at AB will be equals to, all right. So if you stand at this center here, at this point, and you want to take your shear force, all right. So what are we going to have? All right. So if you look at this, we have this upward force, and then we have this uniform distributed load, right? So now we are going to have, we said our upward force should be what? Positive. So we are going to have arrow A here. So we are going to have arrow A. Then we have a uniformly distributed load here. If we convert that to a point load, it's going to be 1 times what? Times Y. So 1 times Y. So you know it's going to be a what? A downward force there. So it's going to be minus 1 times Y. All right. So now here we are going to say the shear force at section AB will be equals to arrow A minus Y, because 1 times Y is nothing but what? Is nothing but Y. All right. We agree that we have our maximum positive bending moments at the point within the span where our shear force is equals to what? 0. All right. So if we equate this equation to be equals to 0, we can get what our Y is. All right. So if we do that, we are going to say 0 equals to arrow A minus Y. So it therefore means that if I move this arrow A to this side, I'm going to have 0 minus arrow A, which is minus arrow A. Minus will go with minus. Then we can say that Y is equals to arrow A. Y is equals to arrow A. And don't forget that our arrow A is what? 5 into what? Into 1 plus S all over what? All over 3. All right. So, all right. So we are going to consider bending moment at support A now. We are going to consider bending moment at support A. All right. So let's just take it like this. All right. So this will be equals to. All right. Now look at our support A here now. So let's consider the bend moment at that point. So here we have a uniform distributed load here, and the distance is what? The total distance is S, right? All right. So now for us to take the take the moment towards point A here, it's going to be a what? You know, if you convert this uniform distributed load to a point load, it's going to be a what? A downward force, right? So now we are going to say 1 times what? S. 1 times, that is minus 1 times S, then times S divided by 2. All right, so this is going to give us minus S squared all over 2. I hope we understand this fully. All right, so now the next thing we are going to do is we are going to consider the bend moment at a distance Y from what? From C. Bending moment at a distance. Bending moment at distance Y from C. All right. You know, we said something the other time that we are going to have our maximum positive bending moment between the span AB, and then we are going to have the maximum negative bending moment at the what? At the support. It can be at support A, and can also be at what? Support B. But since we are taking the distance, we are taking a distance from this point to this point here. So we are taking this our negative bending moment and maximum bending moment to be at support A. Don't know if you understand that. All right. So now we are going to say bending moment at a distance y from C. Let's just say y. All right. So this will be equals to, all right. So this is distance y from C. So we are taking the bending moment towards this side. So now we are having an upward force here, arrow A times what will be the distance here. The distance here is going to be what? Y minus S, because from this point to this point is what? S, and from this point to this point is Y. So this distance here is going to be Y minus S. So arrow A multiplied by what? Y minus S. So we're going to have here to be arrow A into Y minus S. All right. So now we are having a uniform distributed load here. So it's going to be what? Minus 1 times Y. 1 times Y. Then times what? Times Y divided by 2. All right. So that is what we are going to have here. All right. I hope we understand this. So the rest is just mathematics. Okay. Now, we can further rewrite this to be equals to, minus y squared all over 2 plus arrow A into y minus S. All right. So if it is like that, it means that, sorry please, all right. So it means that we can, if it is like this, it means that it can also be like this. So the next thing we are going to do is just to substitute here. All right. We are going to substitute for y, and then we are going to substitute for arrow A. All right. So what is our y? Our y is equals to what? Arrow A. So here we are going to say, let me take it back a little bit. All right, is equals to, what is y? Y is the same thing as 5. So it's going to be 5. So minus 1 all over 2 into 5. Then into 1 plus S all over what? All over 3 all squared plus our arrow A. Our arrow is the same thing as what? Y. So we are also going to have 5 into 1 plus S all over 3, then into Y minus S. Y is the same thing as what? As 5. So we're going to have 5 into 1 plus S, then all over 3 minus S. All right, so that is what we are going to have. So this will be equals to, all right, this will be equals to, now if you look at this critically well, you observe that we have 5 into 1 plus S all over 3 to be common here and there, so we can factor it out. So we factor it out, we are going to have 5 into 1 plus S all over 3, then into, so here we'll still be left with one of this same number here. All right. So but this time around we are going to be multiplying by what? Half. That is negative half. So we are going to have minus 5 into 1 plus S all over 2 times 3 is 6 all over 6. Then plus, so we are factor out this out, which is this here. So we just be left with 5. Just be left with 5 into 1 plus S all over what? All over 3 minus S. All right. All right, so that's it. Now, the next thing is to solve math. Now, the LCM of 6 and 3 is 6, right? So this will be equals to 5 into 1 plus S all over what? 3 into, so here we are going to have 6. 6 in 6 is 1. 1 times this. And 1 times everything here is still this. So let's just clear the bracket. We're going to have minus 5 minus 5s. 6 in 3 in 6 is 2. 2 times 5 is 10. 10 times 1 is 10. 10 times this is 10s. Then this one is over 1. 1 in 6 is 6. 6 times this is minus 6s. Alright, so this is what we are going to have. Alright, so the next thing is we are going to say this is equals to 5 into 1 plus s all over 3 into, so here we are going to have negative 5 plus 10 is 5. Then here we are going to have negative 5s plus 10s is 5s. 5s minus 6s is minus x. All over what? All over 6. Alright, so that is what we are going to have. Alright, so the next thing here is 3 times 6 is what? 18. So this will be equals to 5 all over what? 18. Then into 1 plus s. Then into 5 minus s. Alright, so this will be equals to 5 all over 18 into 1 times 5 is 5. Then 1 times minus s is minus s. S times 5 is 5s. Then minus s squared. Alright, so this will be equals to 5 all over what? 18 into, you can write this as negative s squared, then negative s plus 5s, that is plus 4s, then plus 5. Alright, so this is what we are going to have to be our bending moment at a distance y from what? From C. And the next thing is this. Since we have established that we are going to have maximum positive maximum bending moments at between the support A and what? And B, and then we are going to have our maximum negative bending moment at the end of the support, that is A. We are going to have positive maximum bending moment within the span A and B. You understand? And then we are going to have negative maximum bending moment within at the support. You understand? With either A or B, but we have known that it's going to be what? A, based on the fact that we did our calculation towards point C. Is that clear? All right. So now it means that for this beam to be as small as possible, now we are going to say that the bending moment at support A must be equal to the bending moment at distance y from what? From C. And the bending moment at support A is what? Negative s squared over 2. And then the bending moment at a distance y from C is this. All right, but by the time we are going to be equating these two equations, we are going to neglect this negative sign. All right, so we are going to be doing that while we clean. Going to be equating the two equations, that is this equation here and this equation here, neglecting this sign. So we are going to have 5 all over 18 into what? Negative s squared plus 4s then plus 5 will be equals to s squared all over what? All over 2. All right, so you know that 2 here 1, 2 here is what? 9. If you cross multiply, we're going to have this to be 5, and then you multiply through by 5. I'm going to have this to be minus 5s squared plus 20s plus 25 equals to 9s squared. All right, so by the time you move this to this side, it's going to be plus. So 9s squared plus this, that is going to give us what? 14s squared, right? So we're going to have 14s squared. So we're going to have 14s squared. If we move this to the other side, we're going to have minus 20s. Move this to, we're going to have minus 25. Everything will be equals to what? 0. All right, so you are going to recall from quadratic formula that S is equals to minus B plus or minus square root of B squared minus 4AC all over what? All over 2A. All right, so here our S will be equals to, now you are going to recall carefully that the coefficient of S squared is our A, the coefficient of S is our B, and negative 25 here is going to be our C. So if we do that, we are going to have minus minus 20 plus or minus square root of, we are going to have minus 20 squared minus 4 multiplied by A is 14, multiplied by C minus 25 all over what? All over 2A, which is 2 multiplied by 14. So S will be equals to 20 plus or minus square root of, if you take this, put your square on this, you are going to have negative 20 squared is 400. Then plus, you multiply everything that we have here, you are going to have 1,400. 1,400. Then divided by 2 times 14, that is 28. All right, so S will be equals to, all right, so if you add this together and you take the square root, you are going to have it to be what? 42.42. So we are going to have 20 plus or minus 42.42 divided by 28. All right, so for us to get the value of S here, we are going to be neglecting the negative. So we are just going to go with 20 plus 42.42 divided by what? Divided by 28. So our answer there, our answer is going to be 2.23 meter. 2.23 meter. So that will be the value of S. Of course, if you go with negative 20 minus 42.40, you are going to have a negative answer, even when you divide by 28. And you know, we can never have a negative answer for our what? Our S. Is that clear? So that's why we need to neglect that. So our answer for the position is 2.23 meter. All right. Now that we have known the value of our S, now we cannot get our reaction at A, our reaction at B. Then we can therefore proceed to do the shear force calculation, then the bending moment calculation. Then after that, we are going to draw the shear force and the bending moment diagram. So you can quickly take a screenshot of this while we proceed. What our Y is, our Y is equals to arrow A, and which is equals to 5/3 into what? Into 1 plus S, that is 1 plus 2.23. All right, so it shows that the both values is going to be equals to what? It's going to be equals to 5.38 kilo. Okay, because our Y is a distance, so it's going to be in meter, while our RA is going to be 5.38 kilo Newton. All right, so that's what we are going to have. So our reaction at A, this is it, our Y. So our reaction at B will be equals to 5/3 into 5 minus S, which is 2.23. So by the time you do the math, you are going to have nothing but 4.62 kilo Newton. All right, so now the next thing we are going to do is the shear force calculation. All right, so we are going to be going for the shear force calculation. All right, so if you look at we are going to be starting with point D. So the shear force at point D will be equals to, we stand at point D and look towards your right hand side. We don't have any shear force, so it's going to be 0. So the next one is point B. Shear force at point B will be equals to, now mind you, you stand at point B, you have a uniform distributed load, of which if we convert that to a point load, so here we have 4 minus s. X is 2.23. So 4 minus 2.23, though I don't write it here, but no problem. Let's go. So here we are going to have this shear force, that is 1 multiplied by the total distance that we have here. So it's going to be 1, that is minus 1 multiplied by 4 minus 2.23. All right. So if you do that, you are going to have this to be 4 minus 2.23, that is 1.77. So we are going to have this to be minus 1.77. I don't want to write it this way. All right. 4 minus s, that is 4 minus 2.3, that is 1.77. So we are going to have minus 1 multiplied by 1.77. All right. Now, again at point B, again we are having a reaction at B, right? So we have a reaction at B again. So, and our reaction at B is upward force. Don't forget the reason why this uniform distributed load here at point B, if we convert to a point load, it's going to be a downward force. That is why it is negative. So, and the reaction at B is upward force, is going to be what? Positive. So it's going to be 4.62. All right. The meaning of this is at point B, we have a uniform distributed load which is negative 1.77, and by the time you now add the effect of this reaction at point B to this, is going to change the shear force from negative 1.77 to 2.85 kilonewton. All right. So the next one is point A. So the shear force at point A. All right. So at point A, we also have a uniformly distributed load. Okay. So now, which is going to be, now the distance from here to here is 6. From here to here is 1.77. So 6 plus 1.77, that is 7.77, right? So now we're going to have negative 1 multiplied by 7.77, because it is a shear force, a uniform distributed load converted to a point load, the total distance that it covers. All right. So, and again, we are going to have, at this point A, we have 2 upward forces too. All right. So by the time we add their effect, we're going to have plus, let's start with RB. RB is 4.62 plus RA, which is 5.38. So this will be equals to, so if we add the 2 effects of this upward force to negative 7.77, it's going to change it to what? It's going to change it to 2.23 kilonewton. All right. So, and the shear force at point C, the shear force at point C will be equals to what? 0. All right, because it is an over angle beam. All right. So let's just say this is 0 kilonewton, and this is 0 kilonewton. And if you still want to solve that, you can solve it as well. That is the uniform distributed load 1 multiplied by the total distance, that is negative 10, then minus reaction at A minus reaction at B. That should give us 0. Okay, that is negative 10 plus our reaction at A and our reaction at B. That should give us 0. All right. So now we are going to be going for our bending moment. Our bending moment calculation. All right. So I already have my values here to make the work faster. Let's just all right. So we started with the bend moment at point D. All right. We don't at point D we don't have any force. So of course the bend moment at point D will also be equals to what? 0. All right. So the next one is the bending moment at point B. All right. The bending moment at point B. If you stand at point B here, we have a uniform distributed load converted to a point load, that is 1 times 1.77, that is negative 1.77, negative 1.77, then multiply by the distance divided by 2, that is 1.77 divided by 2. So if you do this, you are going to have nothing but negative 1.06 kilonewton meter. All right. So the next one is the bending moment at point A. All right. So the bend moment at point A. If you stand at point A here, we are going to have RB multiplied by 6. So RB multiplied by 6, then and our RB is 4.62, right? Then multiply by 6. So we are going to have 4.62 multiply by 6. All right. Then again we have this uniform distributed load here, which we are going to convert to a point load. So if we do that, 1 multiplied by the total distance, that is the total distance from this point to this point, is going to be what? 7.77. So it's going to be minus 1 times 7.77, and the distance is going to cover is going to add, it's going to be 7.77 divided by 2. All right, so if you do your math, you are going to have your answer to be minus 2.49 kilonewton meter. All right, so and the bending moment at point C, it is an over angle beam, is going to be what? 0. All right, I've explained this concept to us in our introduction class, that if we have an overhanging beam, the bend moment at the free end is going to be what? 0. And the shear force is not all the time you will say the shear force is 0. When you are dealing with shear force, just check that point, because it's possible we have a downward force here. It's possible. I've solved questions similar to that. And again here, the shear force at this place is better you just solve them, but it's because I have resolved it. Then I have solved it, you can still do it the same way I explain it. Uniform distributed load multiplied by total distance, that is minus 1 multiplied by 10, then plus reaction at A, then plus reaction at B, you must definitely get 0. All right. So now we are going to be using this above information to draw the shear force diagram and the bending moment diagram. All right. All right. So let's start with the shear force diagram. So the shear force, you can see this is the reference line for our shear force diagram. This is the reference line for our bending moment diagram. All right. So and here we have 0, here we have 0, here is 0, here is 0. Above this both line is positive, and below this both line is what? Negative. All right. So let's start with the shear force diagram. Our shear force at point D is 0, so it means this point here is 0. All right. So at point B we have two shear force. The first shear force is negative 1.7. All right. So let's take this as a negative 1.7. Okay. Let's take this point to be negative 1.7. All right. So we are going to join this point to this point. All right. And again, at point B again, by the time we now add the effect of this reaction at B, yeah, it makes the shear force to change from negative 1.7 to what? 2.85. All right. So we have 2.85. So let's take this point as our 2.85. All right. So by the time you join this point, you're going to have something like this. All right. So here again. All right. So that is what we are going to have. Sorry, please. I want it to be darker. All right. So now that's what we are going to have. So again, at point A2, we have two shear force there. The first one is negative 7.77. Negative 7.7. This one is negative 1.7. So let's take this point as our negative 7.77. Let's take this point as negative 7.77. All right. Then by the time you now add the effect of the two upward force there, you change from negative 7.77 to what? 2.23. Don't forget that this one is 2.285. So 2.23 should be somewhere around there. All right. So this force is going to go like this. All right. So all right, that's it. So at point C, said our shear force is what? 0. So I'm joining this point with this point. So please always make your work to be neat. All right. So shade now. So this is positive. This is positive. This is negative. This is negative. So you can shade. Right. All right. So that's it. So this is our shear force diagram. So let's draw our bending moment diagram. All right. The bending moment at point D is 0. And the bending moment at point B is negative 1.06. So let's take this as negative 1.06. All right. So I hope you know why we are using an inclined line here. Not this line. We are using it because we have a uniform distributed load. All right. So again, we are going to be using a curve here. All right. All right. So now we have negative 1. So here it's going to look like this. All right. So that's it. So at point B, at point A, we have it to be negative 2 point something. So let's take this point here. Let's take this point here to be negative 2 point something. And at point C, we have 0. All right. So again, this is going to, you join this. All right. So this is what you are going to have. Now, if we look at this, we know that you can see what I was explaining the other time. We now have a maximum negative bending moment here, which is what? Minus 2.49. Now we are going to have a maximum positive bending moment here. Now where our shear force is equals to 0, which is at this point. Right? So for this point now, we trace a point down. Supposed to go in alignment with this line here, but it's not a perfect let's just go. Let's just take it the way it is. All right. All right. So now this point now, let's call it point E. Let's call it point E. Let's call it point E. So let's calculate the bend moment at point E. All right, bend moment at point E. All right. So if you look at this, you look at this point, we can take our moment towards this side, or we can take it towards this side anyhow. So let's take it towards this side. All right, so the first one that we have here is the total distance is y, and we have a uniform distributed load. So that is going to be what? -1 times y, then times what? Times y divided by 2. And don't forget our y is what? 5.38. So we are going to have -1 multiplied by 5.38, then multiply by 5.38 divided by 2. All right. So again, we are going to have this reaction at A here towards this side. So don't forget, we said the distance from this point to this point is going to be y minus s, right? So it's going to be plus ROA, an upward force, plus ROA. Our ROA is 5.38, then into y minus s. Y is 5.38 minus s 2.23. All right, so if you do your math carefully, you are going to have this answer to be 2.49 kilo Newton meter. All right, so now we can therefore say that 2.49 should be somewhere around here. All right, let it be somewhere around here. So let's join this curve carefully. All right, so let's go. All right, so all right, so just manage it. Okay, let's see. I think I can draw it perfectly than this. Let's go from this point. All right. All right, so this is going to be negative. This is negative. This is going to be positive. All right, so we can shade now. All right. All right, so we are not asked to calculate the point of contraflare, but in case you want to calculate your point of contraflare, so we are going to have 2 points of contraflare here. So one is at this point and the other one is at this point. So this is how to go about the question. Thank you.